Okay, so we're back for week 3 of distance learning, quarter 4. Just want to say thank you guys again for hanging in there and working hard. I greatly appreciate everything you've been doing. We're now taking a look at quadratic data this week. So you guys have gone ahead, you've explored regression in Google Sheets, and you've done some linear data that you found on your own, which is fantastic. This time we're going to take a look at quadratic data. Quadratic data is a little bit trickier, and the reason is it can be harder to come by. Not to say that it's not common. We use quadratic functions anytime we have to model an object in free fall near the surface of the Earth. So if you were to throw a basketball or a baseball or strike a golf ball or hit a missile, I guess you wouldn't hit a missile, you'd shoot a missile. These would all be modeled using projectile motion and parabolic paths. So again, very, very common that we use these. Just you might not be interested in any of those. From a business perspective, you guys learned this year in economics about supply and demand curves. And a lot of times we can model the demand curve using quadratic equations. So that's an extremely practical application. This tends to work better when you're working with fewer units. So it's usually better modeled for smaller local businesses. But if I'm doing a large national company, it'll be more similar to what you saw in your class where it's exponential functions that we use to model the data. But regardless of applications, here's some data I pulled, okay? So this right here is data that we get from striking a baseball with a bat at varying degrees and measuring the distance it lands from where it is struck. So we have to make a couple assumptions here. We're going to assume that the speed of the ball is constant every time it is thrown, and we're going to assume that the force that the bat imparts to the ball is the same every time. Okay, so with those two assumptions, we get this set of data. Okay, so this wasn't generated by me or an equation. This was actually observed and recorded. It was not me hitting the baseball because I don't have that level of accuracy. But this is my data set. So my independent variable here is my angle, which is measured in degrees, and the distance the ball travels, which is measured in feet. Okay, and if we go ahead and put in a quick chart here, I can quickly see that it's kind of U-shaped. So it kind of looks like a parabola. Let's go ahead and clean this up. We're going to change it to a scatter plot. Okay, and then I'm also going to go here to the series, and let's play with a few things here. The first thing we're going to do is we're going to add a trend line. Okay, now you notice immediately it does a linear trend line, but what we're actually going to take a look at is a polynomial regression, or a quadratic regression. Now remember, quadratic is just a polynomial of degree 2. Which fortunately it goes ahead and defaults to here. If I was doing a cubic regression, I could change this to 3, quartic, looks like it skipped quintic, but I've got a couple different options here, okay? But here, a degree 2 is a quadratic regression. So I get a pretty good line, all right? We're going to go ahead here and show the r squared, okay? And we're going to use the equation. And when I do that, I can see, look at my r squared value. It's almost 1. So that means that this line accounts for a ton of variability in this data. So this is a really good fit here, okay? Now the other thing you'll notice about this equation is they write a little bit backwards to how we're used to seeing it, okay? So I'm just gonna go ahead and throw this up here so it's out of the way. When we take a look at a quadratic, we're used to it being in the form of y equals a times x squared, right? Sorry, let me clean that up for you. This is a times x squared plus b times x plus c. So this is what we're used to a quadratic looking like. So what I'm going to do is I'm just going to go ahead and copy these variables, and we're going to use this form of an equation. Again, I apologize, it should be a c. I'm having a hard time typing tonight. So the variables I need to know are the coefficients, a, b, and c, because everything else is my input or my output variable. So a, if I read up here at this top equation, is whatever's in front of x squared. So up here, x squared, I can see that a is negative 0.174. Okay, so there is my a value. B I can read is the number in front of x, that's 14.5. Okay, and then c is this negative 21.9. Okay, and now that I have these numbers in Excel, I can actually build an input-output machine, right? So I'll have my input value here. I'll have my output value, which will be right here. So we'll just go ahead, we'll make up an input, we'll put something like 27 degrees, right? So there's my input, which would be an independent variable, 27 degrees. Now for my output, I'm going to build a calculator. So I'm going to say this output column, I want to equal my a value So I click on the number for A. You'll notice in the equation it references where that's located at, times my input value, x, right, squared, plus my linear coefficient, b, times my input data, right? So again, I-15 again, right? And then finally, plus c. I hit enter. And what this now does is, as I change this input cell, it'll update my output cell. So here's 27 degrees. I could assume if I were to hit it at 27 degrees, which would be somewhere around here, it would go somewhere around 250 feet. And right there we got 242.754 feet. So now my calculator works. And I can dynamically change this input cell. So I go ahead here and put, 32 degrees. What will that do for my distance? Well, it increases it slightly to 263 feet, right? And maybe I'll go to 50 degrees and see what that does. 268 feet, so even better. Maybe I'll go to 60 degrees. Does it keep increasing? Oh, sorry, I put that in the wrong spot. 60 degrees. Does it keep increasing? No, it goes back down, okay? So again, I've got my input-output calculator now. Now, maybe I want to find the vertex here, right? Now, to find the vertex here, we actually have a formula that we've used before, and that formula is negative b over 2a. So I want that to be my input. So I'm going to go back to my input box. Instead of just putting an arbitrary number, I'm going to put another formula. So I hit equals. I'm going to type in negative, and again, I'll click on the reference cell for b, divided by 2, divided by a. Now, if I hit enter, this should give me the vertex's x value. So according to this data, 41.6 degrees, or roughly 41 2/3 degrees, is the optimum angle at which I can strike the baseball to maximize my distance. Okay. Fun fact, we know this empirically from projectile motion physics, that it is 45 degrees, not just, empirically, but also algebraically. So it's going to be 45 degrees is actually the best, but this is pretty good data. I know at 41 2/3 degrees, it'll go to the maximum of 280.183 feet. Okay. This means I can also express my equation as a quadratic and vertex form. So my equation could also be expressed as y equals, a value is not going to change, so it's still going to be this negative 0.174, right? But now in parentheses, I'm going to do x minus h. Now my h value is this 41.667, right? Close the parentheses, squared, right? And then plus k, so plus 280.13. Sorry, 183. So here I've got my equation both in standard and now also in vertex form, and I can interpret the vertex telling somebody, hey, at 41.67 degrees, you will maximize your output of 280.183 feet. Okay, so I'm going to ask you guys to do something similar on your own this week. You're going to have to go ahead, find your own quadratic data. You can search for this online, or you can actually record a video of yourself, maybe throwing a ball using your camera and using some object in the background for height and setting up scale factors. That can be a fun, long project. And once you have your own data, you're going to run a regression, come up with an input-output machine. You're going to make at least one prediction. You're also going to use negative b over 2a to find the vertex, and you're going to interpret the vertex in the context of your data. Same thing with your prediction machine, right? So if I go back and just change this to any number like, hey, 35, my prediction would be if I were to strike the ball at 35 degrees, I would expect it to go 272.45 feet. So that's how we interpret it in the context of our data, all right? So that's going to be your task this week, all right? Email me if you have any questions or need any help, but you guys seem to be doing really well with this. All right, take care. Bye.